All right, let's take a look at another CSES problem, inversion probability. So this is another probability problem. So what's going on here? We have some array of length n, values x1 through xn, and we chose each of those values randomly between 1 and some bound that's different for each index. Right, so in the example, we have a length 3 array. The first value was chosen between 1 and 5, the second value chosen between 1 and 2, and the third value chosen between 1 and 7. And we want to find out the expected number of inversions in this array, right? Expected over the random choices for the elements. So what is an inversion? An inversion is a pair that's out of order if you were sorting it from low to high, right? So it's a pair where the first number comes before in the array, but it's bigger in value than the second number. And we want the expected number of those, right, as we randomly fill out this array. So how do we do this? So it's actually another linearity of expectation problem using indicator variables. So if we define an indicator variable for each pair, which is whether or not it's inverted, then the number of inversions is just the sum of those indicators. Linearity of expectation says the expected number of inversions is just the sum of the expectations of each of the indicator variables. And the expectation of an indicator variable is just the probability that the thing happens. So we just want, for each pair, to sum up the probabilities that that pair is inverted. Right, so this is nice. Now we've reduced the problem basically just looking at each pair independently, and then we can add up all the values. So how do we actually find out whether or not a pair is inverted? It obviously depends on the upper bounds for that pair. So how many ways are there to fill out the values? Well, there's Ri ways to choose the first value and Rj ways to choose the second value. So there's Ri times Rj ways to choose them both. And each of these is equally likely, right? Because it's uniform. So we just need to count the number of those pairs that are inversions. So how do we do this? So one idea would be to just check all the pairs. But that's actually kind of too slow, right? How many pairs are there? There's like n squared. It's like 100 squared. And the r's can be up to 102. So if we just check all the pairs, there's Ri times Rj. That's like 100 to the 4 running time, which is it's dangerous, right? To do 100 million in 1 second. Maybe you could do it. But actually, we can shave off a factor of 100 by, instead of enumerating both numbers, we can just enumerate the first number. And then, to be an inversion, we would want the second number to be smaller. How many ways are there to do that? Well, it has to be smaller than the first number and up to the bound of the second number. So there's that many ways to choose the second number to be smaller, which would, each of those counts as an inversion. So, instead of enumerating all the Rj, we can just, in constant time, figure out how many give an inversion. And this gives us 100 cubed running time, which should be fine. So that's the idea. Let's go ahead and actually code it up. Vector stood as usual, we'll want doubles for probability. Okay, so the inversion j has to be bigger than I. So we'll start j is I plus 1. That's our answer. So we want to find out the number of inversions. And we'll just follow the strategy of enumerating the first pair, right, from 1 to Ri. And we said the number of ways the second number could be chosen smaller than it. Min of whatever value we have minus 1 and Rj. So the probability that's inverted is this divided by the total number of possible pairs, right, Ri times Rj. And we just add up those probabilities to get the answer. And we want 6 decimal places. Yeah. But 6. 0.057143. Cool, looks good. Okay, so that works. So again, the code is pretty short. We just need to sort of figure out the right way to think about this. So linear expectation to say that we treat every pair independently, and then to actually compute the probability that any given pair is inverted. It's just a counting problem, right? There's Ri times Rj possibilities. How many of them are inversions? This many, right? We can brute force over the first number because we have enough running time, and then we want to know how many ways there are to choose the second number smaller than it. So it has to be smaller, and it has to be up to its bound. And then just divide, the number of ways to get an inversion by the total number of ways to get the probability. Right? Probability is just counting. Add up those probabilities, get the answer. So that's the problem.